So today we'll be talking about our work on building new dispersion functionals for using density functional theory. We do this in a way where we try to introduce dispersion without distorting the electron density. And the formalism has been named the fixed diagonal matrices, or FDM formalism. So I did this work together with Timo Beckman and my supervisor, Paola Gori-Giorgi, here at the VU in Amsterdam. So the work I will show today is published in the 3 papers that are listed below. The first one from JPCL contained really the idea and some preliminary calculations. The Faraday discussions goes more into the mathematical background, derivations of functional derivatives and so on. And the JCTC, the third paper, is really a benchmark set where we compare to other methods. And the code we used to do the benchmarking is available from my GitHub, so it's listed below. So I just want to start briefly with what is dispersion? Well, if you consider 2 monomers, A and B, it could be atoms, they could be molecules, they could be nanodots, and they are separated by a large distance r, then we can define the interaction energy as the difference between the energy of the complex AB at this distance r and the energies of the 2 isolated systems. Then often what we do is we consider the limit of large separation, and then we recover a power series in 1 over r plus some exponentially small terms. This power series in 1 over r corresponds to the multiple interactions, but also the induced multiple interactions and the induced multiple interactions. Then these exponentially small terms correspond to charge overlap and exchange. Then what we do is often is to expand the interaction in orders because it's weak. And then at first order, we obtain the electrostatics, the permanent multiple interactions. The first term, 1 over r to the third for neutral systems, is the dipole-dipole interaction, while the second order term corresponds to induction, which is the induced multiple interaction, and dispersion, the induced multiple interaction. And the dipole-dipole term corresponds to 1 over r to the 6th. And this is the kind of the famous term that you have in your Lennard-Jones. It's the famous term that appears in a lot of DFT approximations for dispersion. So how do we treat this formally? We partition a Hamiltonian in 3 parts, the 2 parts corresponding to the isolated systems A and B. So these are many-body Hamiltonians, including also the Coulomb interaction between the electrons in that system, and a remaining term which corresponds to the Coulomb interaction between the nuclei and the electrons on the different systems. And this depends on the distance between the 2 systems. Then again, considering the limit of the large separation, we get this Hamiltonian as a power series in 1 over r exactly. So the usual course of action in this kind of intermolecular theory is that for large r, you start with the isolated systems, and then you correct this using Redi-Schrödinger perturbation theory. And we typically work in the polarization approximation. We ignore antisymmetry. Our Hilbert space is then the tensor product of the Hilbert spaces of systems A and B, and not the properly antisymmetrized wedge product of the 2 systems. There are, of course, theories such as symmetry adapted perturbation theory, where these effects are taken into account, and then you get these exponentially small exchange terms as well, in addition to the polarization terms. But we are in DFT, and in DFT, we don't treat dispersion with Rayleigh-Schrödinger perturbation theory. Instead, we need a functional for it. So this is just to summarize what we always do in DFT, at least formally, is that we have the total energy as a functional of the external potential. So as a functional of your nuclei, basically, the positions and nature of the nuclei. And you minimize overall possible densities, which are fine, the external potential and the universal functional F. Here I write the universal functional F in the Levy constraint search format, so that you search over all wave functions which yields the density rho, and you search for the one minimizing kinetic energy plus VE. Then this universal functional in the Kohn-Sham formalism is split up even further into 3 parts. Kohn-Sham kinetic energy, TS, the U, the Hartree energy, which is the classical electrostatic energy of the charge density, and the remainder, which is basically the unknown part, at which you always need to approximate the exchange correlation function, as is well known to most of you. Now, where are intermolecular interactions here? Well, our electrostatics and induction are mostly covered by Hartree and the external potential. although, of course, when you have induction, you need to do a certain self-consistent cycle to get an induction effect. And this means that you need to get the exchange correlation locally correct to get good induction, but at least already the physics is mostly there. Dispersion, however, is really something that just comes into the exchange correlation functional, and it's quite difficult to approximate because it's a very non-local phenomenon. So most of the functionals we use in practice are based, at least in semi-local functionals, LDAs, GGAs, and meta-GGAs. And those have the unfortunate property that since they are local, when you try to do a system which consists of two systems at a reasonable distance, you get the exchange correlation energy of the two isolated systems plus a correction which goes exponentially due to the density overlap. And this, of course, cannot capture this famous 1 over r to the 6th, 1 over r to the 8th, 1 over r to the 10 that second order dispersion has. The same holds for hybrids, but not for double hybrids, because when you introduce some MP2, then you will also introduce some dispersion. So usually, how do we remedy this? Well, we take our exchange correlation functional, the one without dispersion, so the one with the semi-local functional or the hybrid, and we add on a dispersion correction, which typically also depends not only directly on the density, but also on the internuclear distances of the two systems. There's quite a large amount of different functionals. Here I list a review of Stefan Grimme from 2016, which covers, I think, most of what is there, but a lot of people have worked on this problem. And typically the ones that we use, at least in quantum chemistry, they rely on using free atomic dispersion coefficients and or dynamic polarizabilities, and then somehow correcting those for the molecular environment that the system is in. In solid state physics, there is also another category of functionals which is quite prominent, which are the von Waals density functionals and recently the modified Fido von Voorhis functionals. And those are in principle not depending so much on parametrizations from free atoms and so on. So those are really almost pure non-local density functionals. So what is the issue with the large amount of functionals that are there still? Typically is that they are isotropic. This is, of course, something that always happens when you start from some free atomic quantities, is that it's quite difficult to then introduce some anisotropy in there. But we do know that anisotropy is sizable. If you look at, for example, the C6 dispersion coefficient for hydrogen-hydrogen, you will find that it depends something like 10% on the orientation of the two molecules. Also, typically, the self-consistent effect on the density from the dispersion functional is not considered, but the relevance of this is somewhat unclear. There has been some controversy about how dispersion appears in the density, because the Hellman-Feynman theorem demands that there is a density change at order 1 over r to the 7th, which produces the correct force. But this is a very small distortion of the density that can be very hard to capture. And it seems that in what we do, we don't get this density distortion, but we do get the correct energy out. Okay, so then to introduce kind of our approach is I will introduce it somewhat pictorially. So we're working in density functional theory, and that is why we always use a real space picture. So in a real space picture, induction is quite easy, right? So here I have two atoms A and B, and atom B here induces a dipole moment on system on atom A, and that's it. So you, in the electron density, you have a complete picture of how this works. Dispersion is complicated. Say I have two perfectly spherical atoms, then the electron density will not distort in such a way that you get some nice attractive dipole, because symmetry simply forbids that. So how can we solve this? Well, we have to go one step further. We need to look at the pair density. So now instead of, we take the wave function, we square it, and we integrate out the coordinates of electrons 3 to n, and we leave 2 electron coordinates. Then we can look at a picture of dispersion. So here, to make it easy, I did it just 2 particles in 1D. So on the x-axis is the location of particle 1 relative to its nucleus, and on the y-axis is the position of particle 2 relative to its nucleus, and the color indicates the magnitude of the pair density. So red means high pair density, blue means low pair density. In the limit, the intermolecular pair density simply reduces to the product of the two isolated densities of the two systems. However, when they get a little closer, then this pair density starts to get skewed here in the positive x direction. So they both go to the same side of the nucleus. And you can, in 3D, you have this kind of usual picture where they want to be based on the dipole-dipole interaction. They either want to be at positions A, B, C, or D, essentially. And you can calculate your dispersion energy directly from the first order correction to your pair density. But if you then have a pair density correction, then you can say, okay, what is the change in the electron density? Because the pair density integrates to the electron density. So this is the pair densities I have showed you, but what I didn't show you is that they both integrate to the same density of the unperturbed monomer. So both correspond to the same electron density, but we can capture dispersion in this way. And this seems like a kind of a simple idea, right? This is used a lot in DFT. We have a different object, a different pair density, but somehow we do have the same shadow, the same marginal, same electron density. So, I mean, this is similar idea to Kohn-Sham, where you also have a system with the same density, but there is a different pair density. But now, how can we easily encode this in a wave function? And essentially what we did is just take this and then take the square root. So you have the two densities and you have this 1 plus j, and you just take the square root. So that's this. We will start with two 1-electron systems. We will move to more electron systems, but basically the concepts, the ideas are the same. So it's easier to do it without the clutter of the notation of all the different electrons. What we do is we take as this wave function ansatz product of the ground state wave functions for system A and B, this phi naught, and we add on this correlation factor, the square root of 1 plus j. So for example, for two hydrogen atoms, phi 0 would be your 1s orbital. Then we wanted to fix this electron density. So this constraint we put in the following way. So we take psi, we take absolute value square, we integrate out 1 electron coordinate, and we get phi 0 squared or rho a, and similar for B. Due to the square root format, this leads to a simple linear constraint. So if you integrate j with the correct density, so here rho b with R2 and j of R2, or same for rho a with R1, then you need to get 0 in all cases. That is the constraint we build in. Now, of course, this j itself, you can try to optimize over it, but we prefer, of course, using one particle basis. And because what we use are not really orbitals, we have called them dispersals. And these dispersals are these functions b, bia, and bg, b. And then we introduce variational parameters c to optimize over later, to optimize the energy. Now, we still need to take care of this, this density constraint, and we do that by a Gram-Schmidt orthogonalization procedure. So how does that work? So these functions in B are actually written in terms of another set of functions f, and we subtract this integral of f with the density. And using this trick, you get that whenever you integrate this dispersal B with the density, you get 0. So it's basically, for orbitals, this would be Gram-Schmidt. And then, of course, there is these functions f, which need to be chosen a priori. They're really a basis for this dispersal space. Then we have taken care of the density constraints. So now we can do an unconstrained minimization of the expectation value of the kinetic energy and the interaction Hamiltonian. Note, there is no external potential present because we are fixing the electron density. And so the expectation value of the electron of the external potential remains the same. And we subtract out the values for the uncorrelated system. So T0A is the kinetic energy of system A, isolated, etc. And E electrostatic is just the permanent multiple interaction between the two systems. So now we need our matrix elements. The interaction energy is easy because the interaction energy is a multiplicative operator. So we only get this linear term in J because we square root of 1 plus J, and we get this linear term in J. So you get an integral with the densities, J, and this interaction, R1, R2. You can make it just a Coulomb interaction if you want. Kinetic energy is somewhat more complicated because you get these derivatives of square roots. And then we get an integral with, again, the densities and the nabla square of J, of R1, R2, and of R2. With in the denominator this 1 plus J. Then in practice, we always simplify this by approximating this denominator as 1. And this corresponds to the basically to something like a second order perturbation theory. One caveat here is that it's all only valid if 1 plus J is larger than 0 in all of space. This would be a problem if you were treating J fully variationally at finite R, but fortunately, this is not an issue if you are working perturbatively. So when you just truncate this kinetic energy, then it's fine. Now that we have our matrix, or now that we have our matrix elements, we transform to this dispersal basis, right? So we had J before, and now we expanded in these expansion coefficients C, and then matrix elements of this dispersals. So W here is the interaction. It's linear in the coefficient, in the expansion coefficient, and we have a quadratic term which corresponds to the kinetic energy, where tau is really the kinetic energy element between these dispersals, and S is an overlap element. And this looks, of course, a lot like what you know from orbitals, except that there is a weighting factor corresponding to the density present here. Now you can optimize this, right? Because it's just a quadratic energy. So optimizing it leads to solving a linear system of equations. But we can do something a lot cheaper by, well, for example, diagonalizing S. So in this dispersal basis, we do an orthogonal transformation diagonalizing S. This leads to a minimization that becomes a so-called Sylvester equation, which is this is what we did in the original paper in JCPL. But then afterwards, I realized that you can actually also diagonalize tau with S as a metric. So you diagonalize the kinetic energy matrix with S as a metric, so the generalized eigenvalue problem. And in that case, you can directly solve for the coefficients. Namely, the coefficients are -4, and then the interaction divided by the sum of the kinetic energy of the two systems, of the two dispersals. Now, because you're doing a generalized eigenvalue problem, this means that the cost is cubic in the number of dispersals of both systems. And this is the most expensive step. And if everything after is cheaper than that. So then, of course, you want to know that this works, right? So our FDM dispersion energy is then given by -2, and that is sum with the interaction squared divided by the kinetic energy. And this is, of course, very similar to what you usually get in second order perturbation theory. So you have the matrix element of the interaction on top squared divided by the difference between the energy of the excited state. So for just hydrogen, I have the results here. So these are for C6, C8, and C10. So the first 3 dispersion coefficients. And we compare to work from Takar in 1988 and to work of Mazzilli in 2008. And we find that we can get almost all digits correctly. So for C10, it's completely correct. Then there's one digit which is wrong for C8. Then for C6, we had a little larger discrepancy, but it turned out to be that the result of Takar was not as accurate, and the result of Mazzilli was slightly more accurate. So then there is the issue of these functions f that you need to choose, these dispersals. So here we used a series of powers in radial distance r and then a spherical harmonic, because that works nicely with the spherical symmetry. And here we look at the convergence, so the C6 relative error with respect to Mazzilli as a function of the number of terms that you include on the x-axis, and then on the log scale on the y-axis is the error. So you see it converges very rapidly. And again, so the cost is cubic in number of terms on the x-axis. So that works really, really well. But of course, we're interested in systems with more than one electron. So we slightly modify our wave function ansatz. instead of having this one electron function, we now have the ground state many-body function of both systems multiplied. And with x underline, we denote the spin and spatial coordinates of all electrons in either of the two systems. And our correlation factor is now altered in the following way. So we take a square root of 1 plus a sum over ij, and then the interaction between all these pairs. So the density constraint then produces the same condition. And we can expand this function j again in a one particle basis of dispersals, etc., etc. And basically everything stays the same with only two differences. This interaction element w, it now also contains terms in the pair densities, and the overlap now also contains terms in the pair density. So then, of course, you can now expand the interaction again in a dipole-dipole, etc. And this leads to dispersion coefficients in terms of the monomer pair densities. Now, this is not entirely what we wanted, right? We wanted the density functional, not the pair density functional. But you can then approximate the exchange correlation hole as a density functional, and you can move over to a density functional. Accidentally, also what happens is that the density constraint enforces fixed pair density on the monomers, and the three-body density and the four-body density, etc., etc., etc. So really what we're doing, if you look at the constraint search type formalism, is that we're actually minimizing overall wave functions that yield the many-body densities for the two systems separately. So this is a stronger constraint than only acquiring the densities. What is an advantage is that there is no change in the electron-electron interaction on the monomer. And this makes for quite a large computational saving because we don't need to consider the most difficult aspect, really. So now to some results which we got with this method for the many electron case. So on the top right, I now have the functions fi expanded in these Cartesian monomials. And here on the left, we have our C6 value with respect to our reference C6 value from dipole oscillator strength distributions. And we have then the three colors correspond to the three types of monomer pair densities that you considered: Hartree-Fock, MP2, and CCSD. And of course, as we progress down this series from Hartree-Fock to MP2 to CCSD, you increase the cost, but you also increase the accuracy, and that's what we see here. So Hartree-Fock clearly heavily overestimates in both cases. Well, MP2 and CCSD do quite a lot better. And CCSD actually tends to underestimate, at least for the molecules. So the mean average percentage error for atoms and molecules with Hartree-Fock is huge. It's more than 50%. So that's clearly not reasonable. For the atoms with MP2 or CCSD, we get around 12%, which is mostly due to the fact that a lot of the atoms are open shell systems, and that we do not do well for open shell systems for reasons that unfortunately we do not understand yet. Then there is, with the molecules, we get better results with MP2, 7.9% and 7.2% for CCSD. Still, these results we're trying to improve them. So working together with the group of Chiara Capelli in Pisa, and they are now doing Gaussians for these dispersals. And that seems to improve the results quite a bit. So actually it makes, because we are variational, so improving the basis means you only go up. So Hartree-Fock actually gets worse, but CCSD, because it's undershooting a little bit, quite improves due to this expanse in the dispersal basis set. Another interesting thing to note is that the Hartree-Fock does so bad, while there is another method in the DFT, the exchange dipole model by Becke and Johnson, that performs quite well. And also uses the exchange hole, just like we are doing here now. But there are a different set of approximations which are invoked. And yeah, we definitely do quite bad here with Hartree-Fock. Then interesting for DFT is, can we do a self-consistent density from this? So yes, we can. We derived this in the Faraday discussions paper, so you can calculate the functional derivatives. And now here, the elements with the dots are the functional derivatives of the matrix elements transformed to the dispersal basis, in which tau is diagonal and S is as well. So these are expressions that involve the dispersals and the functional derivative of the exchange correlation hole. Can be computed, but yeah, there is a somewhat lengthy derivation in the supplementary material of this reference of the Faraday discussions. It's not so pretty, unfortunately, but the end result, I think, is quite promising. Yeah, a side remark. So in what we are doing, we are fixing the density. So we are not allowing the external potential to change. So if you look at the components of C6, whether they come from the interaction Hamiltonian, whether they come from the external potential, whether they come from the kinetic energy and the zeroth order Hamiltonian, you can apply the Variational theorem. And in an exact framework, you would actually have +6 times the C6 in external potential and -5 times the C6 in the kinetic energy. So we are not even getting the sign right for the kinetic energy because we are raising kinetic energy and it should be lowered. So then you ask what is going on, and then you just do regular second order perturbation theory. Here I did it variationally, but you can do it in several ways. And then you see that it's also off. So you do get a correct sign, at least for the external potential and the kinetic energy, but it's not the correct quantity. So what it turns out to be is that we don't need to satisfy the Variational theorem for the exact energy. All we need is that the ratio of the interaction Hamiltonian to the zeroth order Hamiltonian, those contributions are -2 to 1. That is crucial. This causes a bit of a headache, but basically it comes down to the fact that the Wigner 2n+1 rule is only for total energies and not for all the individual components. Then there's the last topic. So our goal is to use approximate pair densities or exchange correlation holes so that we obtain a density functional. And what we did, for example, was for helium-helium, we did the weak interacting limit with Kohn-Sham and the strong interacting limit. So same electron density, but different pair density. And we found that for helium-helium, with the physical pair density, we got 99.8%. With Kohn-Sham, we got 116%. And SC, we got 32% of the accurate C6. So you quite overshoot if you use Kohn-Sham, and you go very low if you use SC. Then we looked at not only helium-helium, but more systems, and it turns out that the Kohn-Sham exchange hole from density functional approximations performs worse than Hartree-Fock does. So that is not a viable option. So to conclude, we designed a method which yields dispersion coefficients as a function of pair densities. The dispersion coefficient C6 is sufficiently accurate for closed shell systems with no density distortion. And what I should add is that I did not show this in the plot because we had very few systems, but that also anisotropic coefficients had similar accuracy as the isotropic coefficients for the same systems and for the same pair densities being used. And yeah, so the big goal, which is in progress, is to go to a density functional by introducing exchange correlation hole approximations. Okay, thank you very much.